Today again we will talk about another type of codes, error correcting codes called convolutional codes. Again, here we are going to look um, at cases where we have the generator matrix, or rather the generator polynomials, and we see how we generate the code words. Although the code word here is just an interleaving of the message bits and the error checking bits. We will not get into construction of convolutional codes, generator matrices, generator polynomials. As I said, we are going to do that only with the BCH and RS because they have a very elaborate method of creating polynomials of the desired error correcting capability. Yeah. So they don't only check one, they don't only correct one bit error, they can correct whatever number you want. So let's see how these convolutional codes work. So basically that's what convolutional codes do. They map information bits to code bits by sequentially interleaving, that is a keyword, a sequence of information bits with generator sequences. So how you generate the sequences is by using shift registers and combinatorial logic, performing module 2 addition. So normally convolutional codes are specified by these three parameters: n being the code word, length of the code word, k again being the length of the message, and m being the number of memory registers. And k by n is called the code rate, and it's a measure of efficiency of the code. Yeah, because what you're saying is if k is large and m and n is not so much larger than k, then we say efficient, because it will always be larger than k, but not so much larger than k, then it will be more efficient. For example, if k is equal to 1 and n is equal to 3, that is 1 over 3. If k is equal to 2 and n is equal to 3, that is more efficient, 2 over 3. That's what you're saying, because you're taking every 2 bits and then you're transmitting 3 bits in the place of 2 bits. But if you are having 1 bit and then you're transmitting 3 bits, that's less efficient. That's what we are trying to say here. So we are going to restrict ourselves to the case of where k is 1 bit. It means you are taking 1 bit at a time, because k does not mean the length of the sequence. It means the number of bits you are taking at a time. Yeah. So we are going to restrict ourselves to the case where you are only using k is equal to 1. Yeah. And I think the best way to look at convolutional codes is actually to look at convolutional encoder, and we are going to see that actually this process is similar to convolution. That's why we actually call it convolutional encoder. Yeah, it's very similar to convolution. Yeah, because you actually have what we call the generator polynomials and which interact with this shift register. Yeah. So what you have, these are the memory registers, and these are shift register. It means when you put an input here, it goes and it comes out, and another input comes. Yeah. And this is the way it works is you're putting in, these are sequence of bits, but you're putting in one bit at a time. So initially, we'll assume that the convolutional encoder is reset, which means everything is 0, 0, 0. And therefore, the output definitely will be 0, because what you're saying is we are adding what is in U0, what is in U1, and U2. So we're adding these three inputs to this adder. This is a modulo 2 adder. Yeah. So if you add this, it just means that whenever you have an even number of ones, the output will be 0, and an odd number of ones, the output will be a 1. The same thing with this, but now here we are adding whatever is in all the three, but here we are adding only what is in 2. Yeah. So this is a different generator polynomial from this. So in this case, you can see this is G1, generator polynomial 1, which is sometimes what we do. Sometimes what we do is we will say this is 1, and this is x, and this is x squared. Just a polynomial. So these are just our usual x is just our usual. It's not really a variable. I think the correct name is indeterminate. I think that's what we call it. It's not actually a variable. It's just a placeholder for bits. I think the correct word is indeterminate. X is neither a variable or indeterminate. Determinant, no, it's determinate, not determinant. Yeah. So you can either represent it this way, or you can even represent it the other way around, so long as if you stick to a convention, you stick to it. So normally we can call this 1 plus x squared, x to the power of 2. Or you can even use the other way around. I don't know in this case what we have. Oh, I don't think we have even called it in the names. Yeah. So this one, the first one, you can see convolutional encoder shown in figure. This the generator polynomial we are seeing is 111, which actually means 1 plus x, because always polynomial should be given in using this x as a placeholder, plus x squared, and this is 1 plus, this is 0 plus x squared. So those are the two. So you have these two polynomials. One gives you the output of these three. Or the V1 is mod 2 U0 plus U1 plus U2. Yeah. So it's simply, this one is this plus this plus this, and this one is U0 plus U2, because we are considering this one. That is V2. So now our output, so you are putting in, for example, this was 1, 0, 1. So what you're going to put out will be 6 bits output, because each of these bits is represented by 2 bits. But it's not that you are going to find out when you put 1 what is the output, followed by when you put 0 what is the output. It will not be that straightforward, because what happens is this one will be, that's why its convolution will be sliding. Sequence will be sliding through these memory registers. Yeah, actually that's why it's called convolution encoder. It's basically a convolution process. If you remember, we looked at convolution last semester, and we looked at it last year. It's from your syllabus. So that is your output. These are the two outputs. And let's see how this one is used to. Now we see how it's used to encode. But let's see how after encoding we are able to detect. We look at the process of encoding, and then we look at the process of decoding. Yeah. So this one, you can represent it in many ways, this process, and you look at the different ways. So you can represent it as a state diagram. This is a state diagram. What we are saying, we consider these two bits. You whenever you put a bit, the other 2 bits are considered to be, they determine what is the output, but they are kind of just memory. Yeah. Otherwise, the actual bit you put is this one, but this one still influence the output. And these 2 bits, we call them the state of the encoder, because this is what you're putting in, but this one is already the state of the encoder. Yeah, you're putting in this, but this will be the state of the encoder when you put that U0. Yeah, when you put the bit into this U0. So we call this the state of the encoder. Yeah, so we can have this state. So this can be 0, 0, because the state bits are 2. So this can be 0, 0, 0, 1, 1, 0, or 1, 1. So we can represent this. Yeah, this is actually, we call it is a finite state machine. Yeah, so to speak, because it has got these 2 states. So whenever you put a bit, it just adds to this state, and then it gives you an output. It is a code with memory. Yeah. So you can represent it as this. These are the states, 0, 0. Yeah. And I'm sure you have come across the state diagram in the past somewhere. This is 0, 0. This is the other state is 0, 1. The other state is 1, 0. And the other state is 1, 1. And we are saying if you have state 0, 0, where we are here. If you have a state 0, 0, then this input is a 0. Forget what is here. This input is a 0. That means the next state will be a 0 because this is a shift register. Will be a 0, 0. So this is 0, 0. Every time a bit comes in, then the bit that was here moves here, and this one which was here moves here. So if this is a 0, so that will be the current state because we consider this to be the state. Yeah. The next state will be 0, 0. So be now this one will be here. This will shift this way. It's a shift register, and then this will shift this way. So the next state will be 0, 0. Yeah. So you can see if you are at 0, 0, the next state will always be 0. So it will be still the same state. It will be still 0, 0. Yeah. And where the input is 0, we put that continuous line. So in this case, that is a continuous line. It still remains itself. I mean, it still remains 0, 0. Yeah. But more important, so what is the output? Let's see. If you have 0, 0, and then you put 0, it means the output is 0 plus 0 plus 0, which means it's 0. And the same thing, 0 plus 0 is 0. So the output is also 0, 0. So we represent the output here. So output is 0, 0, and the state is still the same state, 0, 0. That's why we do like that. So that is if the state is 0, 0. What about if the state is 0, 1? If the state is 0, 1, it means this is, let me use this, that can be sure, can be okay. So if this is 0, 1, and then your input is 0, so this is the state. The next state will be 0, 0 because this will come here and this will come here. So if the state is 1, you put in a 0, the next state will be 0, 0. So we come back here. If it is this one, the next state is 0, 0. So then whenever you put a 0, you have a continuous line. The next state is 0, 0. Yeah. The next state is 0, 0. And what will be the output? Let's see what will be the output. So you have, so this is 0. So this is simply 0 plus 1, which is 1. And this is 0 plus 1, which is 1. So the output will be 1. Yeah. And of course, you can do that for all of them. So that makes a state diagram. And yeah. Oh, this is 0, 1. Okay. Let's say, because we are looking at different states, and the state is what is in these 2 bits. So we dealt with the first is the state was 0, 0. Now we are looking at 0, 1. So we are saying if it is 0, 1, and then the input bit is 0, then first we can be able to get the output. The output is 0 plus 0 plus 1, which is 1. And this output, that's V1. And the V2 is 0 plus 1, because it doesn't have this middle one, which is also 1. So the output is 1, 1. But to which state do you go to? Because if there's a state, if you move now next, because you're talking about the next state, the next state will be 0, 0, because the next state is this one will come here, and this will come here. It will be 0, 0. So if you are in 0, 1, then the input is a 0, which means this is a continuous line. It will take, the next state will be 0, 0, and the output will be 1, 1. Yeah? Let me do maybe all of them, then it will be easier to understand. If the input is a 1, oh, actually even here I didn't look at the 0, I should have looked at the 1. Actually, sorry for that, I did not look. Even the other case, when it was 0, 0, we looked at the case whereby the input was a 0. Suppose it was a 1. If it was a 1, then the next stage would have been 1, 0. And the output would have been, yeah. Sorry, I'm going back, so I hope I don't lose anybody. Now that he has asked a question, I'm going back to the 0, 0 case. We saw when you put a 0, what you get. But suppose it was a 1. If it was a 1, it means the state is moving from 0, 0 to 1, 0, because this will come here and this will come here. The output will simply be 1, 1, because 1 plus 0, 1 plus 0 plus 0 for here, and 1 plus 0 for here, it will still be 1, 1. That's why we have this. It will go to 1, 0. The dotted line means the input is a 1. Yeah. And this will be 1, 0, and the output is 1, 1. So this represents the output. This represents V0, V1. The two outputs, this one's here. Oh, it's V1, V2. Sorry. So we used to V1, V2. Yeah. So that was the case. Now in the case of 0, 1, of course, when you put a 1, you can also likewise find that it goes to the state 1, 0. If it is 1, 0, you can see if you put a 1, it goes to 1, 1, and the output is 0, 1. And if you put a 0, it goes to the direction of the arrow. It goes to 0, 1, and the output is 1, 0. If it is 1, 1, if you put a 0, the state remains 1, 1, but the output is 1, 0. If you put a 1, if you put a 1, that's what it means the same. If you put a 0, it becomes 0, 1, and the output is 0, 1. Yeah. So that's a state diagram, representation of a convolutional encoder. Does anybody have a problem with the state diagram representation? And we will see why we prefer although today it doesn't matter, it's just probably easier to see things from a trellis. We'll come to trellis, but I'm just mentioning it because we'll try decoding when we reach the trellis. Yeah, but you can represent your data as this for because it's a finite state machine. You can use a state diagram like this one. Yeah, you can use a tree diagram. Yeah. The difference between a tree and the state diagram is just that in this case we consider whenever you put in a 0 you go up, whenever you put in a 1 you go down. Yeah. So you can assume you are what we have done here, and which we normally do a lot, is to represent the state so that you don't have a problem of mixing the outputs with the state. We like calling this state A, this state B, this state C, and this state D. But you don't have the confusion of zeros, 0, and 0, 1. So we leave this to the outputs. Yeah, yeah, to make sense. So that's what I was saying here. Let's say we say 0, is state A. So we are talking about state A. Yeah. If you are in state A, the 0, state, and then you put in a 0, the output will be 0, and you remain in state A. Yeah. Remember here where we say you are still in state A. Yeah. And if you put a 1, you go to state C, and the output is 1, 1. This is this one here. Yeah. Then you can see this tree just I think there's a place it will reach, it will just begin repeating itself. Of course, once you get to A, this one does not. Yes, so when you go to A, the next time, if you are at A and you put a 0, you go to A, but this becomes a C. Yeah. Oh, yeah. Even here it will be a C. This is a C. Yeah. And a C, this becomes B, and this becomes D. Yeah, we need to look at what happens. Oh, yeah. When you're at B, yes. So I think this one gives you all the possible, because what you want is this is like a lookup table, so to speak, that you can be able to check if you are here, where would you expect to go if this was the input? Because that's a concept we are going to use later to decode. Yeah. So I think after this point, you can see you have all the possibilities. Yeah. Because the possibilities are you are state A or state B and state C and state D. And then for each of those states, there are two possibilities. The input is a 0 or a 1. And that's why you get all that after when you have got these 8 outputs, different outputs. This represents all the possibility. This is the possibility of A with state A with a 0, state A with a 1. This is state B? State B with a 0, state B with a 1. This is state C with a 0 and state C with a 1. And this is state D with a 0 and state D with a 1. So we have, at this point, we have all the possibilities. So we don't need to keep on drawing the tree further. Yeah. So we are going to see later when you are decoding. That's when now you need to draw the tree as the inputs are coming in. Yeah. But we are not going to look at how you decode this tree. We are going to look at the case of where you are using the trellis. It's easy to explain the principle with the trellis. So for this particular encoder, for this convolutional encoder, the tree diagram, the state diagram is this one. It gives you all the possible states and what is the output when the input is either a 0 or a 1. Yeah. Then that is tree. That's the tree for this one, for this encoder. Now we are going to draw now um the what do you call it? And it's important even when you're doing the trees, sometimes it's easy to just to do the state table for the encoder. We call this the state table for the encoder. Yeah. So the state table has got the input bit, register contents. Of course, register contents are important for you when you're trying to work out the output. But the state for this register content, the state is at time t1, yeah. Oh, this is not, yeah, ti. As time ti, whatever time you start counting, yeah, at time ti is 0, 0, which is this, which is state A, and at ti plus 1, that is when this 0 moves here, becomes still 0, 0. Yeah. The output calculated from here, we know the algorithm here is 1 plus x squared, so it is adding all the zeros, they still be 0, and then adding this 0 and the first 0 and the last 0 is still 0. Then we go to the easiest way to do the state table is consider this state A and look at the two possibilities. Yeah, being a 0 or a 1. Consider state B and look at the two possibilities. Yeah. Then consider state C and look at the two possibilities. And then you look at D and look at the two possibilities. The two possibilities are 0 and 1, and this 0 and 1. And I think the process is straightforward. That will give you the output, which means doesn't mean if you put 0, 1, 0, 1, 0, 1, you get this. Yeah, it's a bit more complex than that. We are going to see when we actually plot a sequence. Is this table clear? The input bit states register contents, state at time ti, and state at time ti plus 1, and that's the output. Of course, this is because it's a 2 output, because you could be having a 1 by 3, because there's a 1 by 2, because one input bit with 2 output bits. You could have a 1 by 3, you could add another bit. Yeah. So that one would just be adding this and this. Yeah. And again, we want to look at the error correcting capability of this encoder, because it actually depends on these algorithms. Yeah. But since we are not getting into the generation of the algorithms, we just see how it actually detects and corrects the errors. But this, of course, when it's 1 by 3, it's supposed to have better error collecting capability. Yeah. So those are the two representations. Now let's look at the third one. So the first thing you start with is create the state table. Yeah. Then from the state table, you could be asked to create maybe the trellis or the tree or the state diagram. Yeah. Does anybody have a question on this one? I normally ask because sometimes it looks very easy when we are doing it, but when people are told to do the state table, they are unable to do it in an exam situation or a CAT situation. That's why I was asking, make sure that you have understood it, because the main thing is you are dealing with states, and then you have different states of the encoder, and the state of the encoder means the number of register excluding the first bit, because actually in most cases they don't even put this as a register, but then they just put this as like that, so they will not be showing like a register. Yeah. So the important registers are these two registers, and they are the ones that determine the state, the length of the state. If we had three of them, then the states will be more. It will have 8 different possibilities of states, and therefore your table will be a bigger table to have 16, because of the 8 states. You can have a 0 or a 1, so you'll have 16 entries in this table here. So assuming everybody is okay with that, then we can go to the trellis.
Excuse me.
Yeah.
I wanted to ask on the state diagram.
Yeah.
Could you just move? I can see that there are some lines that are dotted. Are they dotted? Ama they are just. Is there a difference?
Yes, there's a difference. In the state diagram, you are trying to show what is a 1 and what is a 0. And in the state diagram, if the input is a 0, we have the continuous line. And the input and the if the input is a 1, you have the dotted line. Because you have to show the difference between, there must be a way of showing this is a 1. Otherwise, you could simply write maybe input 0. But we say we just show in a state diagram, if the input is 0, you have a continuous line. If the input is 1, you have a two-dotted line. And we are going to use the same convention with the trellis. Yeah. In this one, tree,
Okay,
we don't use dotted. We use either going up or going down. Is that okay? Okay.
Yes. Thank you.
Yes, Samuel.
Yes, we said we restrict ourselves to 1 bit at a time, but I was wondering how would it look like if, let's say, we had 2 bits going in at a time?
Oh, okay. It will be a different table altogether, because it will mean now we'll still be doing the same. But what we will be doing is, let's see. I'm not trying to draw the one of 2 bits at a time. It will just mean 2 bits are coming at a time. Yeah. But still, the state will be these ones. But of course, it will change the input. because 2 bits at a time, it means in this scenario, after this goes, and you have to put 2 bits at a time, it means the 2 bits are coming here. So 2 bits must come out. So it will be, these 2 bits were here, they will be here. Yeah. You get it? But now you may not be able to represent it as a state diagram. No, you can still present it as a state diagram. You just have more states. Yeah. Because you have the 2 states, but now the 2 bits can be 0, 0. Now there are more inputs, possibility of the bits 0, 1, 1, 0, and 1, 1. So we are going to look at the case where this is 0, 0, and then you have all those possibilities. When it is 0, 1, then all these possibilities, actually there will be no difference. 1, 0 with all the possibilities. So it will be, you'll be having 16 entries in your state diagram. It will not change anything. Yeah. Because now for every clock, 2 bits are considered. Yeah. So the 2 bits would have to get into the state. Yeah. I've not tried to draw these different diagrams for the state, but it's not complicated. It will just be different. Yeah. And it works, but the algorithm, we are going to see later that we don't, the ones for 2 bits, the implementation is a bit complex, so they are not normally used. So sometimes you prefer to use parallel ones, 1 by n, so that k is always 1, a number of 1 by n encoders, instead of using, for example, instead of using a 2 by 3 encoder, you implement 2 1 by 3 encoder. Yeah. Yeah. So we are going to see that after the end of this presentation. So this is a trail list for that because what it is doing, it is giving us all the states A, B, C, D, and then it is giving us for each input what is the output. Yeah. So you can see if the state is 0, 0, and then your input is a 1, no, sorry, a 0, continuous line, then your state still remains 0, 0. I think I missed here. You're using the same encoder. No. Oh, it's 0, 0, sorry. Oh, even 0, 0 and there's a 0, of course it remains 0, 0. Even the output is 0, 0, yeah. It's okay. The output is 0, 0. But if it's a 1, then the output becomes 1, 0. No, 1, 1, sorry. It becomes 1, 1, and it takes you to state 1, 0. The output is 1, 1, takes you to state 1, 0. So these are the 2 possibilities. If you are in state 0, 0, you can either end up in state 0, 0 if the input is a 0, or if it is a 1, you can end up in state 1, 0. If the input is 0, 1, then it means, I mean, not the, if the state is 0, 1, and you input a 0 bit, that means to take you, the output will be 1, 1, and it will take you to 0, 0. If input is 1 bit, then it will take you to state C, and the output is 0, 0. If you are in state C, and the input is 1, the output is 1, 0, and it takes you to state B. If it is 1, it takes you to state D. Yeah? Takes you to state D, and if it's 1, 1, and you have a 0, it takes you to state B, and the output is 0, 1, and if it is 1, 1, and you input 1, you remain in state D. And you can remember, remember here, you remain in state D. These are the only cases where you remain in the same state. Where in the case of D, when the input is a 1, and in the case of A, when the input is a 0. If it's a dotted line, it is not dotted. Yeah. So that is a trellis for this particular encoder. Yeah. This is what you call a trellis diagram. And it helps us a lot to understand how the encoder works, how the decoder works. So let's see how the decoder works. Yeah. Let's consider an encoder and state table of the encoder given in figure 1. We have explained that transitions caused by a 0 are indicated by solid branches, while transitions caused by 1 are indicated by, oh, sorry. I'm not seeing this. Dotted. I think you can call it dotted. Yeah, different branches. Symbols indicated on each branch are output symbols generated by the encoder. I think now we have understood that. Yeah. An example from the state, it is seen that if the state of the encoder at time t is 0, 0, the input 1 is fed to the encoder, then just explaining what I've been explaining. So if you have this sequence, for example, let's see what happens. Let's draw the trellis for this before we go to the so if this there's something I'm not showing very well. There's a diagram I did where I drawn this. I forgot to, I think I removed by mistake. Because we want to see, let's say you received, well, at the receiver, we don't know what was sent. Okay? So we don't know what was sent at the receiver. But this is what is received, this. Yeah? I think 100001. Let me see whether this is what we have here. It's different. Yeah, actually, what I had done, I had drawn, and I think I deleted it. I had drawn this one. I had drawn this sequence. If this was the input, what I was trying to show, if this is the input, you can have you can draw your you can draw your sequence on this on trellis. And what I was trying to show is if there's an error, I think let's do it again. Zero one zero 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 one zero zero. I'm trying to memorize. Oh, the only thing. Oh, this is 00010100. So the only thing I think it is this. Yeah, 00010100. Yeah. I was trying to show how you detect an error. So I had drawn the case where the input was this, and of course the output will be this, and then we were showing suppose one bit changed so that now the output is 10. Can we be able to detect that error? Yeah, that's what I was trying to show, but we don't need that actually to demonstrate this concept. This is what you have received. You don't know what was sent. Yeah, you have no idea. The only thing you have is this thing here, which is you can either use this one here or you can use this one here as a lookup table. That's the only thing that is leading you. Yeah, the lookup table. So you receive 1 1. When you receive 1 1 and you are starting here at 0 0, because before everything was reset. So it means we assuming we are starting from 0, everything is reset. So you receive 1 1 because we are analyzing this input. We are saying the input is only that sequence. So the sequence we are working with here. So it has been reset, so it is 0 0. So we start, so we assume we are starting as 0 0, state A. If your input is 0, what do we expect? We expect if the input was 0, we don't know what the input was. You see, we don't know what was the input. Yeah. But we are saying that we have received 1 1. So we have two possibilities. If we received 1 1, since you are coming from 0, if what had been sent, if what was meant to be sent was a 1, when you're in this state, you would have received 0 0. Sorry, if it was a 0, you would have received 0 0. Yeah. If it was a 1, would have received 1 1. So what we are going to do, we are going to calculate some branch metric. Since this is 1 1 and it corresponds to 1 1, so this branch, the metric is 0. The metric will be 0 if it is the same. These are 2 bits. So the metric will be 0 if what you have here corresponds to what you received. If one of those possibilities is what you received, the metric will be 0. If one bit is different, the metric is 1. If both bits are different, the metric is 2. Normally we use a bigger metric to mean the bad situation. Yeah. I think it comes from the fact that normally we use like delay. More delay is bad. So we like using the bigger number so smaller number to say to represent the better metric. I mean the better condition of that particular metric. So in this case, we are saying if one of the outputs is the same, if the output in a branch is the same as this one, then that branch has 0. If it differs with this one by 1 bit, then it is 1. If it differs by 2 bits, then it is 2. So we have a branch metric. So here we are going to consider something called the branch matrix, and then the path metric. I was looking for that word. Branch and the path. Yeah. The path will be the cumulative metric. That is the path. So this branch is 2 because 1 1 differs with 0 0 by 2. 2 bits are different. Or rather, by now you know what we call that. We call it the distance. The distance between this and this is 2. So the distance between this and this is 0. So this becomes 0. And this becomes 2. Those are the only two possibilities because we're only there. So we could have gone here or here. Now when we reach here, of course now we have to look at both. Because now we are here and here. So let's say we are here. So the two paths are still possible. We are not saying that we are not made up our mind yet. Yeah? But we'll see how we make up our minds. So this is 2. Now the next is 1 1. So 1 1, again you can see whenever you are here and you add a 0, you go this way, and when you add a 1, you go this way. So it will just be like here, just be the same. Yeah, isn't it? So but now this is 1 1 and this is 0 0. So the difference here again is the distance again 2. So if it is 2, now the path metric, because this branch metric is 2, so the path metric will be 2 plus 2. Yeah. So this becomes 4. This is 2. This is 1 1. Again, distance is 0. So this will become 2. So for this one, this becomes 2 and this becomes 4. Let's look at this other one. This other state. Because now there are 2 states, possible states here. So this is, if you had put in a 0, because we don't know what we had put in. That's what we are saying. We don't know. Yeah. This is what we have received, but we are trying to decode and to get what was actually sent. Yeah. So this is 1 0 and this is 1 1. The distance is 1. This was 0. So the branch metric is 1. So the path metric becomes 0 plus 1 is 1. Yeah. The other possibility is it could have been a 1. Because that's what we are saying. We don't know. So we are looking for actually this thing is a most, do you call it most likelihood? Most likely, I'm missing the word, decoding, you know. So we are saying what is more likely. That's what we are doing here, and we are getting the matrix to decide now which is most likely. So this one is 0 1. 0 1 again, the metric is 1. because this 1 1, the distance is 1, because this is the same and this is the different. Distance is 1, so the weight, I mean the branch metric is 1, and therefore the path metric is 1. 0 plus 1, 1. So now we are here. We have to look at all the 4. So here, this is 0, 0. This is 0, 0. So this branch metric is 4. So it can be 4. And normally, of course, if you are calculating the best way, just write 4. Yeah. Then you can cancel it out. It can be 4 because of this. And then this one is 4. Now, this is 2. This is 0, 0. This is 1, 1. The output here is 1, 1. So the difference is 2. So this ideally should be 6. Yeah. It should be 6, ideally. Yeah. If you're only considering this one. But now, we can get there through an alternative path. We have this path. This path, this was 1. This is 1, 1. So the path metric is 2. So this is 1 plus 2, which is 3. So 3 is better than 4. So you can eliminate that 4. And there's another thing you do also. The moment you do that, you also need to eliminate this path. It's not a viable path. You remove it. Because you have seen another path. That does still mean it's a path, but we have seen a better path. It has removed this path to get there. Then this, you are here, this is 1, this is 0, 0, this is 0, 0, have to come this way. So this means the branch metric is 0, 1 plus 0 is 1, so you have 1. And remember, we had said it was 6, so you can remove 6, because you have a better path. That path was giving us 6. So you can even remove this, actually. Remove this. Not a viable path. We call it, we are eliminating the path. Because the final path, we call it the survivor path. So that's why we are talking about eliminating, and we end up with the survivor path. Yeah. So we have eliminated it here, we have eliminated here. Now, we have only looked at the 2 cases. Let's look at now from 2. From 2, this is 0, 0, this is 0, 1. So the branch metric is 1. And already we have a path metric of 2 here. 2 plus 1 is 3. Oh, it's 3 and this is 3. I think maybe 3 is what came later. Yeah, I did 3 here. So it will be 3. Let's write 3. We can eliminate it. Then, so that is 3. And this other one, now we are here. So that is 3. And this is 0, 1, and this is 0, 0. So distance is again 2. No, 1. The distance is 1. So this becomes again 3. Let's write the 3. Then we go to the last one. Now we are here. We have written this to be 3, 3. Now here, we are still here 0, 0. If the output is 0, 1, the distance is 1. So this 1 plus 1, 2. It eliminates that and eliminates that part. See? Because here we are eliminating parts. Now this was 2, it became 3, but this was 1. This distance is 1. 1 plus 1 is 2, so it eliminates the 3 and eliminates that part. Yeah. Now we go to the next one. Now we are here. So we are here, we have a path of 3. This is 0, 1. This is 0, 0. So this is a distance of 1. So 3, this will become 4. Yeah. Then this is 3. This distance is 1 again. This will become, this was 3, this will become 4. Yeah. We come here. This is 2. Distance is 1. So this will be 2 plus 1. This is 3. Remove 4. So you have 3, and therefore it eliminates that path. So you're only remaining with this path here. This other one, this is 2. Now which is which? I think this is, whenever you're going this way, this is 0, 0. Yeah, this is 0, 0. So again, distance is 1. So, this was 2. Yeah, this was 2. I think I had mistaken and used this one. I think these are 0, 0. So whenever you come here, this is 0, 0, 0, 0. This is 0, 0. Actually, this should be 3. Yeah, the correct answer should be 3, because we have seen this was 4, but now we have seen that there's a better path, a 3. So let's remove the 4, we put 3, because this is 2 plus 3. 2 plus 1 is 3. Then we come here, this is 1. So this is 0, 1, and this 1, 0. So the distance is 2. So 2 plus 1. So far we have been having 1. 2 plus 1. This is 3. Actually, this is 3. I don't know how I've done this. So this is 3. And this one, this is 1. This is 0, 1. It's the same as 0, 1. So the distance remains 1. So this is actually 1. Yeah. Yeah. And we come to this one. Did you eliminate anything here? No. That was, this was 2. That was 3. Yeah. Yeah. We have not gone to the last one. So now we are here. We look at this one. The distance is 2. I mean, the path metric is 2. And this is 0, 1. And this is 0, 1. So the path metric is 2. Actually, this becomes 2. Remove this. I don't know why I'm not seeing that. This is 0, 1. This is 0, 1. So that is 2. It remains 2. So this path has become better, and it has removed that path. Now, this is 2. This is 0, 1. This 1, 0. That's a distance of 2. So this is 4. So if I remove this path, it goes 4. I don't know, I put 4. So this is 1. Yeah. So now up to here, the path metrics are 3, 2, 3, 1. Actually, my earlier one was wrong. I don't know what I was doing. Then the next one, we look at the next one. This is 3, 0, 1, 0, 0. So this is 4. Because of this, the distance is 1, so that will be 4. Yeah. And then this is 3. This is 0, 1. This is 1, 1. The distance is 1, so this will be 4. Yeah. Okay, let's write it. 4. We come here. This was 2. The distance, this is 1, 1. The distance is 1, so this will be 3. We've seen 4. Now it is 3. Let's remove this, and therefore, how do I remove this root? I even removed the wrong root. This one I should have removed, not this one. Because this is giving us 3. It is this one which is giving us 3, not the other one. This gives us 3 from 2 to 3. So the survival part is this one. This is not a, this is a survivor, but it will not survive for long. Then we, so that we have, that has become less. So now this, we are 2, this is 0, 1, this is 0, 0, distance of 1, so this becomes 3, and therefore, my elimination was completely messed up. This eliminates this part because we had gotten this 4 through here. Now we have a better thing, the 3. So this is 3. So we have 3 here, 3 here. Let's see whether things are going to get better. Then we come here. When we come here, this is 3. This is 0, 1, and this one 0. The distance is 2. So 3 plus 2 will become 5. Unless our root becomes is improved, it's 5. This is 3. 0, 1, 0, 1 is the same, nothing changes. So this becomes 3. So this is 0, 1, and 0, 1. So 3. Then let's look at this one from here. The metric is 1. This is 0, 1. This is 0, 1. So the metric here is 1. And this one, we had gotten 3. And we are 1. We are 1 here. So 1 plus 2 is 3. We are still 3, so both are 3. So actually here we can't eliminate any. I eliminated this one, I don't know why, but I can't eliminate. But it may not be on our path, you see. Now we do the last step, 0, 0. So this is 0, 0, so 3 remains 3. Yeah, this is 3, this 3, then this is 1, 1, this becomes 5. Yeah. This is, what is this? Then we go to this one. This is 1, 0, 0, so it becomes 3. Doesn't change. It still becomes 3 because of the 2 bits change. And this was 1, this is 3. Then this one, it will become 5, but this is 1, and this is 0, 0, 0, 0, so this is 1, and we remove that part. Let's remove that part. Then we come here. This is 3. This is 1, 0. So this should be 4. This is 3. This is 0, 1. So branch metric is 1 plus this 4. Then we go to this one. 3. This is 0, 0. This is 0, 1. 4. It remains 4 because that is 3 plus 1 is 4. And this is, oh, we found this to be 1 somehow. Eh? Why did you get 1? Oh, no, it's 3. And where this can't be 1. It's 3. No, just cancelling this. So this is 3. This becomes 4. So now we can see now our path metrics. So the lowest here is 1. So now with 1, we start here. We can't go this way because this part was eliminated. So we reach here. We can't go this way because the part was eliminated. Now we reach here. We can't go this way, part was eliminated, we go this way. When we reach here, a part was eliminated, we go this way. And here we have no other path, it's only this path. this path. So the actual base we should have received was 1 1 1 0, because this is 1 0, this is 1 0. You see, it is even able to correct with the number of bits. No, this is 0 0. This part is 0 0, sorry. This is correct. 0 0, this is only one that's changing into 1 0. 0 0, this is 0 1 is correct. 0 1 is correct. 0 0 is correct. So, and of course you can see, because if you remember the actual, this is the other one I had drawn was actually this one. Yeah. So this is the correct path. It means, or rather, what we are saying, we had sent this. We had sent this. We received this, but we don't even know what we had sent. But we are saying this. No. We sent this. We are supposed to get this, but we received. What did we receive? We received this. We don't even know what was sent. All we are saying, this does not seem to fit onto the correct path. The correct path should be this one. That is what fits on the path, not what we had. Yeah. Because we are saying, if we are here, that can be only be the state we can go to. And that can be the only output. So we are saying, if we are getting anything else, it's not the correct one. But if it's not the correct one, which is the most likely? That's what this algorithm does. And this algorithm we have used is called Vitabi algorithm. The guy who came up with it, his name was Vitabi. Vitabi algorithm. The algorithm I just applied, the one of applying the branch matrix and the path matrix, was discovered by Vitabi. So we call it the Vitabi algorithm. And with that, we can be able to check, to detect what was actually sent without some very convenient method, without having to know what is there. So basically, it's just what we have is just comparators. It will plot the path by comparing. It compares what it has received and what is supposed to receive, and calculate the metric. Yeah. Then add the metrics. It's a very simple decoder. Anybody who has a problem, is everybody okay with it? Yes, someone.
Yes, I think I lost my network for a few minutes, but I have a few questions that will kind of help me consolidate what I've gotten so far. So the first one is, when the encoder kind of sends that sequence, how is it received by the decoder? Is it LSB first or MSB first? And when you are using that algorithm, why did we kind of have to start with the state A00? Do the encoder and decoder agree on which state the decoder should start with? Yeah, I think those are the two that will help me consolidate.
Oh, the decoder 00. You see, when you start transmitting, we assume you are not transmitting. So we assume the encoder is at 00. You didn't have any input. So the I wanted to call it maybe the idle state of the channel is the encoder is at 00. Yeah, you have not sent anything. So that's where the starting point is. When now you put in a bit, now things change. So we always assume you are starting from 0, and it's logical. If the starting point should be 00. Yeah, if that is why when you are starting to transmit, you have not transmitted before, that will be like the idle. That is 00. Yeah, but it will still work even if you started at any time t. Yeah, but in our case, we are saying when you are doing that, when you are doing this, you see, for this, it doesn't matter where you start. Yeah, it doesn't matter where you start. This trellis always look like this. Now here is something you asked, another question: which side you are starting with? Okay, we are doing it this way. This is time. So normally it means you are starting from here, isn't it? Although in most cases, when you draw, it appears like we should be starting from the right. We are starting from, because this is time. Yeah. So we are starting from here, and then we are coming this way. Yeah. Does it make sense? You know, whenever you draw something on when it comes to the transmission, it's normal. Even when you do a sequence like this, it means if that's a sequence, you are transmitting this bit first. Yeah. So we are starting from this side. But of course, there is the concept of and you can start from any side. There's a concept of the big endian and the little endian and the big endian. Yeah. So you can start from each side. But just be consistent. And of course, I can see why you're asking that, because since you're taking 2 bits, it really matters which side you start. The 2 bits will be different when you start from either side. Yeah, but just be consistent from which side you start from. It will work so long as you don't at one time start from this side, at another time start from the other side, and the system will not work. Did I answer your questions?
Yes, thank you. And the last one is, could you kindly explain to me, re-explain rather, the branch, the path, and the survivor?
Oh, the survivor path. Okay, the survivor path is automatic, because the moment you make a decision, because you see, after here, you see, before here, you are getting to a place from only one place. Yeah, but once you reach here, you can get to those places from 2 possibilities. You see, to get here, you can either get through here or through here. To get to here, you can get through here or through here. To get here, either through here or through here. So whenever you have those 2 paths, once you make a decision that this is the path I'm following, that becomes now the survivor path. That becomes now the survivor branch. You know, then the survivor path, you just be tracing back your path along the branches which are still surviving. Yeah, because you can see whenever we had 2, like here we have a choice, it means 4 have to go. The same thing here, we have a choice, we have 4 paths, and we have 8 paths, but only 4 are necessary, 4 have to go. So it makes tracing back our path very easy. Yeah. Yeah. Because the other parts are eliminated. Now the branch metric is, if for example this is the branch metric, is just that metric for the branch, which depends on the distance between the actual and what is expected under that Because whenever we have this encoder, that's what we are saying. Whenever you have this encoder, its trellis is this one. So any output coming from a state should follow within this one. Yeah. So you are comparing what it should be and what it is. So here we have 1, but we are saying if we don't know what it was, but we are saying if it was a 0, this would have been 0, 0. So it means the branch metric is 2 because the distance is 2. So if you add the branch metric of here, then that becomes now the path metric. The path up to here is 4. Yeah. Then the same. So at least I think you understand the concept of the branch. So you get when you add the next branch, you get a path. You add another branch, you get still a path metric because it is a path to get to somewhere. Yeah. But the branch is just this part. Yeah. Then elimination is whichever is bigger, whichever metric is higher goes, and also the part that is giving you that higher metric is eliminated. Yeah. The part giving you the higher metric is eliminated. So you end up now getting, again, you're going to start from the lowest metric. Among these ones, you start from the lowest, and then now you trace backwards, looking at the paths which you can follow. The paths which are not eliminated, go through the branches which are not eliminated. Did it become clearer?
Yes, it has. Thank you.
Okay, very good, very good, very good. Let's look at then we break after this. Let's look at the concept of puncturing. So puncturing is a technique where you can get a name by end rate by using 2 or more single input codes, 1 by n codes, by deletion of some encoder's output bits according to some puncturing matrix. Again, we won't get into the puncturing matrix because your puncturing matrix is very important. What do you puncture? What do you leave out? That's what we are saying. That's a puncturing matrix. Again, we will not get into the puncturing matrices. Yeah. So punctured convolutional codes have low complexity compared to their non-punctured counterpart for the same level of performance. So suppose you want a 2 by 3. So you can use 2 bits with the 3 outputs. Yeah. Like here I've got 2 outputs. So you can create another output. So 2 by 3 would mean you are taking 2 bits at a time, but you are getting 3 output, the 3 output bits. 2 and you get out 3. But what we are saying is instead of doing that, it's easier to use 1 by 3, 2 of them. Yeah. But of course, when you get 1 by 3, yeah. Oh no, we want 2 by 3. You can use 1 by 2. Yeah. You can use like the one we have here. Like this. Like this is a 1 by 2. With this you can get 2 by 3. So if you are having a string of bits, let's say 1 0 1 0 0 1, and I can see somewhere why would you get confused because here I'm assuming this one is one entering first. Yeah, it makes it easier to imagine this one entering first, but it doesn't matter. It could be maybe you're doing the the big endian, so you are starting from this side. And I'm trying to think if you are writing characters. Normally, I think is a big endian. You start with the beginning, because if you are writing characters and you are putting them into a system, do you put this bit first or this bit first? Yeah. So that would depend on, if you put this bit first, you have to put that into consideration in all your other systems which follow. So it doesn't matter which you put first, but always remember that it's a very important decision, because all the systems have to know which bit is being dealt with first in a block. Yeah. So because you can put this first, but when they are at the other end, they are still organized the same way. So this is, you can use 1 by 2, but you can see now you have 4 outputs, but you want 2 by 3. So what you're saying is, so you are putting your, why I was saying this is because now it means you'll be using a serial to parallel converter, like the way we are doing with the modulation. Yeah, with digital modulation, remember we are saying you could do QPSK by taking 2 bits at a time and putting one on the I arm and the other on the Q arm. And we are saying, that's what we are saying here. So you can get 2 bits, you put 1 bit on this encoder and the other bit on the other encoder. Then since you want 2 by 3, you do puncturing. Puncturing is deciding which you are going to leave out. And it's important how you leave out, because we are saying this is the same. They are identical. These are 2 identical single 1 by n. This is 1 by 2 and this is 1 by 2. These are identical 1 by 2. They have the same algorithms. Now the puncturing is whether am I going to leave this out and use this as V1, this as V2, and this as V3, or do I leave this out? That is the puncturing matrix. It's a decision we will not get into. As I'm saying, it's another concept. So you can, but the concept, most important concept to know is, instead of doing 2 by 3, 2 by 3 is more complex than using 2 1 by 2 rate codes. So this punctured is, we also call it perforated codes. So if you left out this, that is a perforated code. That's a 2 by 3 perforated code. Yeah. So one of the bits is not transmitted. And of course, you can produce different rates, because in this case, it doesn't look like you have much choice. But suppose this was, for example, let's say you even had a third one. Yeah. Another one like that. So now you have 1 by 3. You have 2 1 by 3. Of course, now you can end up with 2. It doesn't make sense to have 2 by 4. So that is like 1 by 2. That will be the same performance. But of course, we are not going to get into it, but puncturing sometimes, having a 2 by 4 punctured might have better error correcting capability than 1 by 2. Yeah. That's what I'm saying. You can have 2 by 5, 2 by 4, and even have 2 by 3. Yeah. Just puncture 3 out and leave 3. So it will not be that you are puncturing all these 3. Is you can decide, I use 2 here, and one here, or use two here and one here. And it improve its error correcting capability. So, are there questions with the combinational codes? If there are no questions, the single lesson we have next week, on Wednesday, we are going to do it physical. We do a few examples, but mainly we want also because we are supposed to be we are supposed to have attendance, and I think with the software I'm using, this may not be considered attendance, adequate attendance for the purpose. I think there is a software used by the university. I don't use it. I use this one. I use Google. So we need to meet so that we can sign the attendance up to now. That's number one. And also, it's good that we see each other, and it makes a difference at times when we just meet and do examples on the board. So let's have. I don't know whether you want us to have the single class or we have the double next week. Which is more convenient for you? Is it this 8 o'clock or the 1 o'clock one? Yes, post your registration. Yes, Samuel.
Oh,
You are posting something. Huh?
yeah, I actually lost my internet again. You
Yeah.
explained something about I saw a half and 2/3. Could you kindly?
Oh,
kindly
you missed that. Pole for you about your internet.
yes.
Yeah. What you're saying is, remember, we had said that you can create any code rate. Yeah. For example, you can have 2 bits entering at every time and have 3 bits output. Yeah, that will be a 2 by 3 rate code. But we are saying that is a bit complex. So sometimes we prefer to use a one where you have only one input bit and maybe 1/2, 1/n. Let's just say 1/n in general. But in this case, if you want 2 by 3, you are going to use 1/2. You are going to use 2 1/2. Yeah, and these are the ones we are saying. These are the 2 1/2. Let me remove everything here. Whenever I do that is right now. So you can have, instead of having a 2 by 3, a 1 2 by 3, we have a 2 1/2. But you see, if we do 2 1/2, we are going to get 4 outputs. So this has 2 outputs and this has 2 outputs. We are going to get 4 outputs. But we don't want a 2/4. We want a 2/3. So what we do, we perforate one of the outputs. We leave it out. Yeah, that's what we call puncturing. So another puncturing will be done. Is another theory altogether. How you puncture to get the maximum benefit from your encoders. And we said we don't get into that one. We just accept the concept of puncturing. So the concept of puncturing is another theory. Require a full class. Yeah. So what you are saying is that's what you are saying. You can produce from 1/2, 1/2. You can produce 2/3 because what you're doing, you're picking 2 bits at a time, and or rather you're using a serial to parallel converter. A serial to parallel converter is always a very important. So you're picking whenever you get 2 bits, you collect them together and you put in one here. Maybe the 0 comes here and 1 comes to this other one. But then the puncturing is you decide which 3 bits you are going to take from the 4. Is that okay?
Yes, yes, it's okay. Thank you. And in regard to the question you've asked about the physical class, I'd
Yes.
suggest that we have the 2 hours for 2 reasons, because
Yeah.
we'll be having labs at 10, and also 2 hours will be good enough time to tackle a number of questions.
Okay, very good. Very good. So, does everybody agree with Samuel? 2 hours next Thursday. We'll be going through examples.
That's okay.
That's okay. Very good. So, I hope you have posted your registration and we see you online on Wednesday. Then on Thursday, we do physical class. Have a good day.